Have you ever wondered how fish and other aquatic organisms survive in water without being frozen during winter? Or have you stopped to think how insects like this crawl on water without sinking? Or this famous image which you would have come across on social media, water acting like a plastic sheet. Have you wondered how that is possible? And to answer these questions, my answer is just one thing. That is the hydrogen bonding in water. So in today's lesson, we will be focusing about how hydrogen bonding can affect the properties in water. Hi class! Today we will be discussing about a substance which we use in our day-to-day life, and I won't be exaggerating if I say that all organisms on earth depend on the existence of this substance, and it's none other than water. Alright, so our first property for today will be the high surface tension. Now, as a definition for you to understand, surface tension is basically the ability of a liquid to behave like an elastic sheet resisting external forces. I know when you read this point, you might not understand, you might think what I'm blabbering here, but let me get to the point. Now, this is an image of water, and as you can see, we have the surface of water, and on top of it, it's air, right? And you must be aware of hydrogen bonding in water. Now, in hydrogen bonding, as you can see, there is a high oxygen which is covalently bonded to a hydrogen. Now, this is a water molecule. The bond between this oxygen and hydrogen is a covalent bond, but we are going to discuss about the type of bond between two water molecules. So as I'll draw another water molecule here, we know that oxygen has two lone pairs. As we know, oxygen is a highly electronegative atom, which means that it has the ability to draw the electrons which is shared between this oxygen and hydrogen towards itself. So this makes oxygen slightly negative and this hydrogen slightly positive. The same story happens to another water molecule, which means this is going to be slightly negative and this will be slightly positive. Now, as you can see, these are oppositely charges. So then there becomes an attraction between the lone pair of this oxygen and this slightly positive hydrogen. This is what we call as a hydrogen bonding. Now, moving into this high surface tension. As you can see, water has a very high surface tension. What is this surface tension? It's basically the ability of a liquid to behave like an elastic sheet resisting external forces. Now, if you can remember the picture that I showed you where a swimmer is at the edge of the water and the picture of where water before it breaks up. Now here, this is a layer of liquid and this is a layer of air. We need to focus on the water molecules which are on the surface, because surface tension is basically a force that exists on the surface. So if you look at the water molecules on the surface, hydrogen bonding exists only downwards. Why is that? On the surface, there are no water molecules above it to bond with the hydrogen bonding with the molecules. The molecules are only below it. So which means there is hydrogen bonding existing with the below molecules. But if you take this molecule for an example, this has hydrogen bonding on all sides because there is water molecules around it. But the water molecules on the surface have hydrogen bonding only downwards, which means it's pulling downwards and there's a net force downwards. This creates a high surface tension on water, and when an object tries to come up, it doesn't let it easily. And that is why you see a plastic film created on top of that person's face. So our next property will be density of ice. Now we'll see how the density of ice helps in the existence of living organisms. Now generally, when we speak of solids and liquids, what do we expect in the states? In solids, we see that the matter or atoms are tightly packed closer to each other, right? Making them more denser than liquids. And in liquids, we expect the atoms or molecules to be dispersed far apart compared to the solids. But in ice, that is not the case. Now we'll see how it works in ice. As you can see, it says ice is a 3D hydrogen bonded network. And I'll explain to you how this 3D bond works. So our next property will be the density of ice, and we'll see how this property is going to help in the existence of living organisms. Now, generally when we speak of density, it's basically the weight per kilogram or per cubic meter. Now, when we talk about solids and liquids, in solids, we expect the atoms to be more tightly packed compared to the liquids. And in liquids, these molecules or atoms are slightly far apart, which makes the liquids to have a slightly lesser density compared to its respective solids. But that is not the case in ice. Now let me explain it to you why that is so. As I told you before, in a water molecule, we have two lone pairs in each oxygen atom, which means it can form two hydrogen bonds. Right. So if you take this water molecule, you can see that each oxygen atom or this oxygen atom is bonded to 4 other hydrogen atoms. 2 covalent bonds within the molecule and 2 hydrogen atoms by hydrogen bonding. So surrounding each oxygen atom, there are 4 hydrogen atoms, and that is a network which we call as a lattice structure. And this is a 3-dimensional structure, and this is spacious. Because of the spacious arrangement in ice, the density of ice is lower than that of water. And this makes it possible for the ice to float on water, and thereby during winter, even when water freezes, the ice floats on top of the water because its density is lesser than that of water, making the aquatic organisms survivable during winter. Enthalpy change or vaporization. I know this term might look very confusing, but let me take it simply, right? Now, this is basically the amount of energy that you need to supply to 1 mole of liquid. And I think you might remember what 1 mole of liquid is. It's basically, if you take 1 mole of water, it will have 6.022 into 10 to the power 23 number of water molecules. So if you take that much of water, how much of energy should you give it to make it boil? That is basically enthalpy change of vaporization. And the concept here is that water generally has a high boiling point or higher enthalpy change of vaporization because of the existence of hydrogen bonds. Now, if I have to make it more clear, for any particular liquid to change into vapor, we need to break the intermolecular forces which exist in between them. Now, for example, right, so if we take the water molecule, we know that it has a covalent bond, right? And when we vaporize this water molecule, we don't expect this oxygen and hydrogen to break and go as ions. That doesn't happen in vaporization. What happens is that as these molecules exist, we will be breaking the hydrogen bonds which hold these water molecules together. Because in liquid state, these molecules are closer to each other. So to separate them and to move them into vapor phase, we need to get rid of this hydrogen bond. And how do we do that? By supplying energy. So how much of energy should we supply for 1 mole is basically what we study in enthalpy change of vaporization. So for example, if I have to sketch the structures, right, so you know that water, or let's take water as an example, there are 2 types of bonds, which is the intra and the intermolecular forces. Now, when we talk about enthalpy change of vaporization, where we discuss about changing the liquid water into vapor, we focus on the intermolecular forces, which are the forces that hold 2 molecules together. So if I am to draw the hydrogen bonds, we know that water can form, each molecule of water can form 2 hydrogen bonds, and let me mark that in red so that it will be clear. Right. We focus on giving energy to break this bond. these hydrogen bonds. We are not talking about breakage of the covalent bonds, which is holding the oxygen and hydrogen atoms together. Now, when we talk about enthalpy change, as I said, it's the intermolecular forces. And a common type of force that you see in all the molecules is the London dispersion forces. So that's present in this water molecule as well. But in addition to that, since it has a hydrogen bond, the water, we need to supply a large amount of energy to overcome this London dispersion force plus this hydrogen bonding. So going back into our notes, hydrogen bonded molecules have a high enthalpy change of vaporization compared to the molecules with instantaneous dipole-induced dipole. Now this term, instantaneous dipole-induced dipole, is another term that we use for London dispersion forces, which is present in almost all the molecules. So in addition to that, since water has hydrogen bond, we can expect a high enthalpy change of vaporization. So let me explain this better with examples. Now let us take the group 6 elements, which is oxygen, sulfur, selenium and tellurium, right? And let's talk about the hydrides of these group 6. So let me draw a graph where you can understand it better. Now on my x-axis, I will be drawing the molecules or writing the names of the molecules. Hydrogen, or maybe this is water, and then we have the hydrogen sulfide, and then the hydride of selenium and the hydride of tellurium. Okay, as we go down, as you can see, the cations of these are same, which is hydrogen. But the elements they all belong to the group 6, oxygen, sulfur, selenium and tellurium. As we go down the group, you can expect these molecules to increase in size, which means this hydride will be bigger in size compared to oxygen or to water. So when the size of the molecules increases, the concept is that the London dispersion forces increases, which means the enthalpy change of vaporization will also increase, because when the London dispersion forces are more, you need to supply more energy to break that so that they can move into vapor phase, right? So on this side, if I'm to mark maybe the enthalpy change of vaporization, right? Or you can even consider this as a boiling point, because those are correlated. When the enthalpy change of vaporization increases, boiling point also increases. So you can take it anyway. And to this, I'll be now drawing the graph that we expect. Since the size of the molecules are increasing, we can expect the London dispersion forces to increase and thereby the enthalpy change of vaporization to increase gradually. This is what we could expect in the graph, right? But this is not the case in reality. If I am to show you the graph which exists in reality, it's this, right? As you can see, again we have on our x-axis the hydrides of group 6 elements, and on this side I have marked the temperature. It's the same thing. You can mark it either the enthalpy or the temperature. Look what has happened to the graph. You can see group 6 oxygen, which is water, has a very high boiling temperature compared to the sulfide, selenium and tellurium. From here, the pattern that we expected exists, where it's increasing with the size of the molecules. So we need to expect water to have the lowest boiling point, but in our case, water has the highest. And now I think you will understand the reason for water having the highest is the existence of hydrogen bonds. Hydrogen bonds are very large forces, and to break them, you need to supply a high enthalpy change of vaporization or a higher temperature, and thereby water has a very high boiling point compared to the other 3 elements or the hydrides of the other 3 elements of group 6. So this, I believe, in our today's lesson, you would have got a brief knowledge about hydrogen bonding and how it's important for different properties of water, especially certain peculiar properties in water. Thank you and see you in our next class.